Hi everyone, today I'm going to present a step-by-step tutorial to set up a CFD simulation of a wind turbine using STAR-CCM+. Here we're gonna learn how to set up a URANS-based CFD model for the evaluation of aerodynamic behavior of wind turbines. In particular, a systematic methodology is presented for the generation of a CFD grid with a proper resolution, which provides a reasonable compromise between computational cost and accuracy. The wind turbine model that we're gonna use for this tutorial is the star-regulated, two-bladed NREL Phase 6 horizontal axis wind turbine as shown here. These figures show the wind turbine being tested in the NASA wind tunnel. Here we're gonna use only the rotor of this particular wind turbine as presented here. You can access the geometry using the link given in the description of this video. As can be seen, the rotor diameter is 10.058 meters. The reason to choose this particular wind turbine is the availability of a large amount of experimental data, including local and global variables at different operating conditions. The test matrix encompasses a large number of tests, which are categorized into several test sequences as is observed here. Among these test sequences, here the simulation setup will be performed for sequence S, in which an upwind configuration of the wind turbine is employed. The wind speed is considered as 10 meters per second. Also, the rotor rotational speed, blade tip pitch angle, and the turbulence intensity are kept constant and equal to 72 RPM, 3 degrees, and 0.5% respectively. Note that for this specific wind turbine rotor, the wind speed of 10 meters per second is associated with the onset of a stall, where the turbulent flow around the blades is highly unstable. As a result, this wind speed has proven to be the most problematic condition for the turbulence models to represent correctly. The simulation setup is performed in the following steps. 1. Definition of the computational domain. 2. Definition of the regions. 3. Mesh generation. 4. Checking the mesh quality. 5. Definition of physics, boundary conditions, and solver settings. 6. Definition of monitors and stopping criteria. 7. Post-processing. In the following sections, a detailed explanation about each of these steps is given. So, first, the definition of the computational domain. Definition of the computational domain. First, you need to create a new simulation. Here, you can choose the number of cores to be used in your simulation. This number must be smaller than or equal to the number of cores available in your PC. Go ahead and click OK. From here, you can save your simulation. I'm gonna call it NREL Phase 6 Wind Turbine Simulation. As I mentioned earlier, for this tutorial, I'm gonna use the horizontal axis star-regulated two-bladed NREL Phase 6 wind turbine. You can access the geometry using the link given in the description of this video. You can import directly your wind turbine geometry into your simulation using File, Import Surface Mesh. Go ahead and check parts validity and repair invalid bodies. Go ahead and click OK. You can see the wind turbine model you just imported under geometry, parts. The computational domain, along with its dimensions in terms of rotor diameter d, is shown in this figure. The dimensions of the computational domain corresponds to those of the NASA wind tunnel where the experiments were carried out. This figure also shows the boundary conditions that we're gonna use. The upstream boundary condition is set to a constant uniform wind speed. A pressure boundary condition is prescribed at the downstream boundary. Finally, the boundaries located at the top, bottom, and two sides of the domain are defined as slip wall boundaries. In other words, these boundaries are modeled as frictionless. The present simulation involves the rotating blades of the wind turbine within a stationary outer boundaries. Therefore, the computational domain to model the rotor rotations has been divided into two subdomains: a stationary rectangular subdomain and a cylindrical rotating subdomain, as shown in this figure. The cylindrical rotating subdomain is where the rotor is located. It is rotated with the same angular velocity of the rotor. Based on the recommendations provided in the literature, values of 0.75d and 0.25d have been considered for the radius and thickness of the rotating subdomain. So, to create the cylindrical rotating subdomain where the rotor will be located, go ahead and right click on Parts, then New Shape Part, Cylinder. For the start coordinates, put 0, 1.25725 and 0. While for the end coordinates, put 0, -1.25, 725 and 0. Put 7.5435 for the radius of this rotating subdomain. Click Create. The next step now is to create the outer stationary domain, which represents the wind tunnel. As we are replicating the experiments performed on the NREL Phase 6 wind turbine, the dimensions of the computational domain should match those of the NASA wind tunnel. So right click on Parts, New Shape Part, Block, click Create. Now right click on Block and rename it to Wind Tunnel. Go to Wind Tunnel Properties here and enter the following set of coordinates for corner 1 and corner 2. Corner 1, -18.3, -20.116, and -12.9. Corner 2, 18.3, $150.87 and 11.5. To define boundary conditions on each wind tunnel surface, we need to split the wind tunnel surface. Expand the wind tunnel surfaces. Right click on Block Surface and choose Split by Patch. You can change the orientation using the rotate view option here. In this dialog, we can see all the wind tunnel surfaces. As we select a part surface, the corresponding surface is highlighted in the geometry scene. Select 151 surface and go ahead and rename it to bottom. Then click create. Select 152 surface and go ahead and rename it to inlet. Then click create. Select 153 surface and go ahead and rename it to side. Then click create. Select 154 surface and go ahead and rename it to outlet. Then click create. Select 155 surface and go ahead and rename it to top. Then click create. Close the dialog. Go ahead and rename the block surface to side 2. Go ahead and save the simulation. For post-processing, it is useful to split the rotor surface in various parts using the split by patch technique. So go ahead and expand NREL rotor, NREL rotor body, surfaces. Right click on faces and select split by patch. Click on reset view bottom here. Select 1, 6, and 5 and rename them to blade 1 base. Then click on create. Select 2, 4, and 3 and rename them to blade 1. Then click on create. Select 23, 28, and 27 and rename them to blade 2 base. Then click on create. Close the dialog and go ahead and rename the faces to blade 2. Let's also rename the surfaces of the cylindrical rotating subdomain to the rotating part. So expand the cylinder, then surfaces. Go ahead and rename the cylindrical surface to rotating part. Go ahead and save the simulation. Now we need to subtract the rotating subdomain from the wind tunnel, so go ahead and multi-select both the cylinder and wind tunnel. Right click on one of them and select Boolean. Then subtract. Select the wind tunnel as the target part. And click OK. Right click on subtract and rename it to virtual wind tunnel. Go ahead and save the simulation. Another Boolean subtract operation that we need to perform is to subtract the rotor from the rotating subdomain. So again, multi-select the rotor and the cylinder. Right click on one of them and select Boolean. Then subtract. Go ahead and select the cylinder as the target part and click OK. Again, right click on subtract and rename it to virtual rotating subdomain. To visualize these new parts, right click in the empty space of the graphics window and select hide all parts. Select the virtual wind tunnel node and drag and drop it into the open geometry scene in the graphics window. We can do the same for the virtual rotating subdomain. Go ahead and save the simulation. 2. Definition of the regions. So now we created the parts. We go ahead and right click on them. On virtual rotating subdomain, click on assign parts to regions and set it to create a region for each part and create a boundary for each part surface. And finally here, do not create interfaces from contacts. And click apply. We need to do the same for the virtual wind tunnel. Then close. You can visualize the regions you just created here under the regions node. Go ahead and save the simulation. 3. Mesh generation. To generate the CFD mesh, the computational domain is divided into two regions where cells with different shapes and orientations are used. The region close to the wind turbine rotor and the region far from the wind turbine rotor as shown here. The region near the wind turbine rotor is more critical for CFD mesh generation as the quality of mesh in this region directly impacts several important aspects of the CFD simulations, including the stability of the simulations and the quality of the obtained results. As shown here, in the region near the wind turbine rotor, a set of orthogonal prismatic cells or layers is used to capture the boundary layer near the surface of the blade. To generate this set of prismatic cells, the estimation of the following two parameters is required. First layer, cell thickness immediately next to the rotor surface, and vertical distance from the rotor surface over which the prismatic cells are created, as shown here in this figure. The first layer thickness depends on the target y plus value of the problem. Meanwhile, the y plus value is determined by the fact that whether the turbulence model uses wall functions to capture the near wall turbulence, which is equivalent to y plus larger than 30, or it is capable of resolving the entire turbulent boundary layer down to the viscous sublayer without using any wall functions, which is equivalent to y plus less than 1. To calculate the first layer thickness for the target y plus value, the following equation proposed by White and Corfield 2006 for a turbulent flow over a flat plate is employed. Here FLT is the first layer or cell thickness, and nu is the kinematic viscosity, u is the free stream velocity, and REC is the chord-based Reynolds number, which is determined as follows. Here C is the local chord length along the blade span. Additionally, to generate the set of orthogonal prismatic cells layers close to the rotor surface, we need to estimate somehow the vertical distance from the rotor surface over which the prismatic cells are created. Ideally, the prismatic cells must cover the entire boundary layer on a wall. For instance, here in this figure, we can see the boundary layer close to a wall. The whole prismatic layers should cover the entire boundary layer, as shown here. So the total thickness of the prismatic layers must have the same height as the boundary layer. In other words, the vertical distance from the rotor surface occupied by the prismatic cells must have the same height as the boundary layer. Therefore, to specify this vertical distance, the equation proposed by White and Corfield 2006 to estimate the boundary layer thickness for a turbulent flow over a flat plate is used as shown here. In this equation, delta is the vertical distance from the rotor surface occupied by the prismatic cells layers, i.e. the boundary layer thickness. C is the local chord length along the blade span, and REC is the chord-based Reynolds number. However, in case of a wind turbine, the estimation of the free stream velocity U, which appears in the definition of the Reynolds number and the first layer thickness, as can be observed here, is not a trivial task. In this case, the free stream velocity U has two components. One comes from the rotor rotation, UR, and the other comes from the wind speed, UW, as shown here in this figure. In this regard, the velocity component that comes from the rotor rotation, UR, changes linearly along the blade span, as shown here in this figure, from 0 at the rotor center to the largest value at the blade tip, which is calculated as presented in this equation, where UT is the linear blade tip speed, R the rotor radius, and omega the rotor angular velocity, as depicted here in this figure. Consequently, both the first layer thickness FLT and boundary layer thickness delta vary along the blade span. We use these equations to plot the distributions of the first layer thickness and boundary layer thickness along the blade span, as presented here in these figures. Note that to plot the distribution of the first layer thickness along the blade span, the y plus value is assumed to be 200. As can be seen from these figures, both the first layer thickness and boundary layer thickness decrease from the blade root to tip. Therefore, the smallest value of the first layer thickness is associated with the blade tip. Moreover, the boundary layer has the largest thickness close to the blade root. Thus, to cover the whole boundary layer close to the blade surface with the highest resolution, the boundary layer thickness at the blade root and the first layer thickness at the blade tip are applied over the entire rotor surface. Thus, for the region close to the rotor surface, a set of prismatic cells layers are used to prescribe the desired y plus value over the blade surface through applying the first layer thickness calculated for the blade tip using this equation. These prismatic cells are stretched from the rotor surface over a vertical distance equal to the boundary layer thickness calculated for the blade root using this equation. The relationship between these prismatic cells is established using a geometric progression as shown here. Here, delta is the vertical distance from the rotor surface occupied by the prismatic cells layers. FLT is the first layer cell thickness immediately next to the rotor surface. M is the number of prismatic layers, and R is the stretching factor between the prismatic layers. Thus, by manipulating this equation, we can obtain this relation to estimate the number of prismatic layers, M. Here, Ln is the natural logarithm. So, the only unknown parameter that remains to be defined here is the stretching factor between the prismatic layers, which is shown here by R. This parameter, in fact, is directly specified by the user. It is recommended to use a value from 1.05 to 1.2. Thus, the first layer thickness at the blade tip is estimated as shown here. Okay, 0.001703 meters. Moreover, delta, the vertical distance from the rotor surface occupied by the prismatic cells at the blade root, is estimated as shown here, 0.017298 meters. Note that C, the chord length at the blade root, is 0.737 meters. Finally, knowing the values of the first layer thickness and the vertical distance from the rotor surface occupied by the prismatic cells, we can estimate the number of prismatic layers using this equation. Here, the stretching factor R is assumed to be 1.1. Therefore, we will have the following values for the parameters of the prism layer mesh: the thickness of the prism layer stretching R, and the number of layers. Note that we are going to set up the simulation for y plus equals 200, which is equivalent to the case where wall functions will be used by the turbulence model. To gain more information about the generation of the prismatic layers, you can watch the video in my channel entitled Mesh Generation in CFD, Prism Inflation Layer Mesh, where I have outlined a practical methodology for the generation of the prism layer mesh. You can access the video using the link given at the top right corner of the screen. Another important point for the region close to the rotor is the size of the cells on the rotor surface, as is shown here. Based on the recommendations provided in the CFD community for the simulations of wind turbines, at least 140 cells are required to be used in the chordwise direction over both the upper and lower sides of the blades. Further, the span-wise direction should be discretized using at least 40 cells in this direction. Additionally, for the region far from the rotor surface, the trim cell measure is used. This measure generates a grid which is constructed mainly from hexahedral cells with trim cells next to the blade surface to accommodate the geometry. Let's now create the mesh. Before we start the process of creating the mesh, it is useful to define the interface between the two domains. So go ahead and expand the regions, expand both the virtual rotating subdomain and virtual wind tunnel. Multi-select the rotating part boundary in both regions. Right-click on one of them and choose Create Interface. You can visualize the interface you just created under Interfaces. To create the mesh here, we're going to use the parts-based meshing approach. So under Geometry, right-click on Operations, New, Mesh, Automated Mesh. In this dialog, in the Parts section, select the virtual rotating subdomain. Also, select Surface Remeasure, Automatic Surface Repair, Trim Cell Measure, and Prism Layer Measure. Go ahead and click on OK. Under Geometry, Operations, right-click on Automated Mesh and rename it to Virtual Rotating Subdomain. Again, under Geometry, right-click on Operations, New, Mesh, Automated Mesh. In this dialog, in the Parts section, select the Virtual Wind Tunnel. Also, select Surface Remeasure, Automatic Surface Repair, trim cell measure, and prism layer measure. Go ahead and click OK. Under Geometry Operations, right click on Automated Mesh and rename it to Virtual Wind Tunnel. Under Geometry Operations, Virtual Rotating Subdomain, Measures, click on Surface Remeasure. In the Properties window, set the meshing method to Enhance Quality Triangle and set the minimum face quality to 0.2. Under Geometry Operations, Virtual Rotating Subdomain, Measures, click on Automatic Surface Repair, and in the Properties window, set the minimum face quality to 0.2. Under Geometry Operations, Virtual Rotating Subdomain, Measures, click on Trim Cell Measure, and in the Properties window, check the box for Perform Mesh Alignment. Under Geometry Operations, Virtual Rotating Subdomain, Measures, click on Prism Layer Measure, and in the Properties window, set the distribution mode to Wall Thickness. Also, set both the minimum thickness percentage and layer reduction percentage to 0.01. Under Geometry Operations, Virtual Rotating Subdomain, Default Controls, set the base size value to 1 meter, set both the target surface size and minimum surface size to 0.5% of the base size. Set the number of prism layers to 7. Set the prism layer near wall thickness to 0.001703 meters. Also, set the prism layer total thickness to 0.017298 meters. For this purpose, set the size type to absolute, then set the absolute size to 0.017298 meters. Under volume growth rate, set both the default growth rate and surface growth rate to various low. Set the maximum cell size to 8% of the base size. Go ahead and save the simulation. Under Geometry Operations, Virtual Rotating Subdomain, right-click on Custom Controls, New Surface Control. Click on Surface Control and set the part surfaces to Blade 1, Blade 1 base, Blade 2, Blade 2 base. Under Geometry Operations, Virtual Rotating Subdomain, Custom Controls, Surface Controls, set both the target surface size and minimum surface size to Custom. Under Geometry, Operations, Virtual Rotating Subdomain, Custom Controls, Surface Control, Values, set both the target surface size and minimum surface size to 0.5% of the base size. Under Geometry, Operations, Virtual Rotating Subdomain, right-click on Custom Controls, New Surface Control. Click on Surface Control 2 and set the part surfaces to rotating part. Under Geometry, Operations, Virtual Rotating Subdomain, Custom Controls, Surface Control 2, Controls, set both the target surface size and the minimum surface size to Custom. Also, set the prism layers to Custom. Here, check the boxes for customized number of layers, customized total thickness, and customized distribution. Under Geometry, Operations, Virtual Rotating Subdomain, Custom Controls, Surface Control 2, Values, set both the target surface size and minimum surface size to 8% of the base size. Then click on Custom Prism Values and set the number of prism layers to 2 and set the prism layer near wall thickness to 0.025 meters. Under Custom Prism Values, set the absolute prism layer thickness to 0.05 meters. Go ahead and save the simulation. Under Geometry, Operations, Virtual Wind Tunnel, Measures, click on Surface Remeasure. In the Properties window, set the meshing method to enhance quality triangle and set the minimum face quality to 0.2. Under Geometry, Operations, Virtual Wind Tunnel, Measures, click on Automatic Surface Repair and in the Properties window, set the minimum face quality to 0.2. Under Geometry, Operations, Virtual Wind Tunnel, Measures, click on Trim Cell Measure and in the Properties window, check the box for Perform Mesh Alignment. Under Geometry, Operations, Virtual Wind Tunnel, Default Controls, set the base size value to 1 meters. Set both the target surface size and minimum surface size to 0.5% of the base size. Set the number of prism layers to 2 and also set the prism layer stretching to 1. Set the prism layer absolute total thickness to 0.05 meters. Under Volume Growth Rate, set both the default growth rate and surface growth rate to very slow. Set the maximum cell size to 256% of the base size. Go ahead and save the simulation. Under Geometry, Operations, Virtual Wind Tunnel, right-click on Custom Controls, New Surface Control. Click on Surface Control and set the part surfaces to rotating part. Under Geometry, Operations, Virtual Wind Tunnel, Custom Controls, Surface Control, Controls, set both the target surface size and minimum surface size to Custom. Under Geometry, Operations, Virtual Wind Tunnel, Custom Controls, Surface Control, Values, set both the target surface size and minimum surface size to 8% of the base size. Under Geometry, Operations, Virtual Wind Tunnel, right-click on Custom Controls, New, Surface Control. Click on Surface Control 2 and set the part surfaces to bottom, inlet, outlet, side, side 2, and top. Under Geometry, Operations, Virtual Wind Tunnel, Custom Controls, Surface Control 2, Controls, set both the target surface size and minimum surface size to Custom. Also here, click on Prism Layers and set it to Disable. Under Geometry, Operations, Virtual Wind Tunnel, Custom Controls, Surface Control 2, Values, set both the target surface size and minimum surface size to 256% of the base size. Go ahead and save the simulation. To capture the wake field behind the wind turbine, the mesh is refined within a cylindrical region behind the wind turbine rotor. This cylindrical region has the same radius as that of the rotating subdomain and extends from upstream of the rotating subdomain to nearly 8 rotor diameters downstream of the wind turbine. So under Geometry, Parts, right-click on Cylinder and select Duplicate. Click on Cylinder 2 and set the start coordinates to 0, 80, 0. Then under Geometry, Operations, Virtual Wind Tunnel, right-click on Custom Controls, New, Volumetric Control. Click on Volumetric Control and set the parts to Cylinder 2. Under Volumetric Controls, click on Trimmer and check the Customize Isotropic Size. Then under Values, click on Custom Size and set it to 16% of the base size. Go ahead and save the simulation. Now we set up the mesh for our simulation. Go ahead and click on Generate Volume Mesh from here. To visualize the mesh, right click on Scenes, New Scene, Mesh. To change the orientation, click here, Views, -X, -Z. Right click on Derive Parts, New Part, Section, Plane. Set the origin to 0, 0, 0. Set the normal components to 1, 0, 0. No displayer and then Create. Close the dialog. Right click on Mesh Scene here and select Hide All Parts. Expand Derive Parts, then drag and drop the section plane into the mesh scene. To add the rotor geometry, to the mesh scene, go ahead and right click on mesh scene 1 and select new displayer surface. Under surface 1, click on parts and set the parts to blade 1, blade 1 base, blade 2 and blade 2 base. Click OK. Click on surface 1 and set the color mode to constant. Under surface 1, you can use the color node here to specify the color of the geometry. Use the zoom option here to zoom in the scene. Go ahead and save the simulation. 4. Checking the mesh quality. Here, the quality of the generated mesh is measured through the evaluation of the cell skewness angle and cell quality metric. The cell skewness angle is a proper indicator of the mesh quality and suitability. The skewness angle theta, as is defined here in this figure, is the angle between the face area vector, which here is shown by A, and the vector connecting the two cell centroids. Therefore, it can be easily concluded that the angle equal to 0 is the best, which means that the mesh is orthogonal. In order to reduce the influence of the skewness angle on the results, it is recommended to keep it under 85 degrees. The second parameter that we are going to use in order to check the mesh quality is the cell quality metric. In the cell quality metric, generally flat cells with highly non-orthogonal faces have a low cell quality. As an example, these figures show a good quality cell and a bad quality cell. A cell with a quality of 1 is considered perfect. A cubic cell is an example of such a perfect cell. However, cell with poor quality has a quality approaching 0. Cells with a quality less than 10 to the power of minus 5 are considered bad and should be avoided. To evaluate the cell skewness angle, right click on plots, new plot, select histogram plot. Click on histogram plot 1 and set the parts to regions. Under axis type, click on bin and set the field function to skewness angle. Here in this plot, we can see the number of cells with a specific skewness angle. As can be seen in this plot, most of the cells have a skewness angle smaller than 25 degrees, and also the maximum skewness angle encountered in the computational domain is about 83 degrees, which is an indication of the acceptable quality of the mesh that we have generated. Now, to evaluate the cell quality metric, again right click on plots, new plot, select histogram plot, click on histogram plot 2 and set the parts to regions. Under axis type, click on bin and set the field function to cell quality. To visualize the minimum cell quality encountered in the computational domain, click on zoom selected plot option here. As we can see here, most of the cells have a cell quality metric close to 1, which is an indication of high quality of the generated mesh. Additionally, the minimum cell quality is about 0.02, which is acceptable for a CFD simulation. Go ahead and save the simulation. 5. Definition of physics, boundary conditions, and solver settings. Before I present the physics definition, it is worthy to discuss the question of which turbulence model to choose for the present simulation. As can be seen here, a large variety of turbulence models has been developed with an attempt to close the URANS equations. And this makes the choice of a suitable turbulence model for a specific simulation a bit of a challenge. For further information on this topic, you can watch the video in my channel entitled URANS Turbulence Models. Which should I choose? You can access the video using the link given at the top right corner of the screen. To make the choice of a suitable turbulence model even more difficult, the turbulence models also use two common approaches to capture the boundary layer near the surface of a body. The first approach, which is also referred to as low Y plus wall treatment, is using a very fine mesh with a high resolution to resolve the fluid flow characteristics within the boundary layer. And the second one, which is also referred to as high Y plus wall treatment, is using a coarser mesh to employ the standard wall functions. In the first approach, where no wall functions are used and the center of the first cell immediately next to the wall should lay within the viscous sublayer of the boundary layer, which is equivalent to a Y plus value less than 1. While in the second approach, where wall functions are used, the center of the first cell immediately next to the wall should lay within the logarithmic region of the boundary layer, which is equivalent to a Y plus value between 30 and 500. The first approach provides a more accurate resolution of the boundary layer, so its use is recommended, especially when dealing with flows with strong wall-bounded effects. To make our choice here, we turn to literature. In this regard, the results presented by Abdul Kadir et al. 2017 and Amiri et al. 2020 show that the best predictions for the NREL phase 6 wind turbine aerodynamics are provided by high Reynolds number turbulence models, including a Reynolds stress model as well as the quadratic and cubic variants of the K epsilon model. Note that the use of wall functions has the advantage of eliminating iterative convergence problems and the excessive calculation time. Thus, to achieve a good compromise between computational cost and accuracy, we are going to use the elliptic blending Reynolds stress turbulence model with wall functions. Now let's create the physics and define the physics that we are going to use in our simulation. Under Continua, Physics 1, right-click on Models and select Models. Implicit unsteady. We're going to use a gas, segregated flow, constant density. The flow is going to be turbulent. We are going to use the elliptic blending Reynolds stress turbulence model. Among the optional models, choose cell quality remediation. Click Close. You can visualize the models here. In order to be consistent with the experiments performed on this wind turbine model at these conditions, we need to set the air density the same value as that used during the experiments, which is 1.24589 kilogram per cubic meter. So under Continua, Physics 1, Models, Gas, Air, Material Properties, Density, click on Constant and set the value to 1.24589 kilogram per cubic meter. Now under Initial Conditions, we're going to set the velocity to 10.0471129 meters per second in the y direction. Now under Tools, go ahead and select Motions, right click, new rotation. Set the axis direction to -y. Set the rotation rate to 72.096161 RPM. Here you can also create a local coordinate system and assign it to this rotational motion. This way the coordinate system will rotate with the same rotational velocity as the value you set here. So under Coordinate Systems, Laboratory, right click on Local Coordinate System, New, Cartesian. Select Rotation and set the Managed Coordinate System to Cartesian 1. Now to assign this rotation to the virtual rotating subdomain, under Regions, expand Virtual Rotating Subdomain. Under Physics Values, click on Motion Specifications and set Motion to Rotation. Go ahead and save the simulation. Now let's define the boundary conditions. The boundary conditions that will be used in the present simulation are shown here. As can be seen, at the upstream boundary, a uniform wind speed is imposed, while at the downstream boundary, the static pressure is assumed to be 0. Further, the top, bottom, and side boundaries are assumed to be slip walls with no friction. So under Regions, Virtual Rotating Subdomain, Boundaries, select the rotating part, and under Rotating Part, Physics Conditions, set the shear stress specification to slip. Now expand the virtual wind tunnel, Boundaries, and set the inlet to velocity inlet. Expand the inlet and under Physics Values, set the velocity magnitude to 10.047129 meters per second. On the outlet, we're going to set the type to pressure outlet. Multi-select inlet and outlet, right click on one of them and select Edit. Under Physics Values, expand the turbulence intensity and set the value to 0.005. Now multi-select bottom, top, rotating part, side, and side 1, and right click on one of them, then select Edit. Under Physics Conditions, set the shear stress specification to slip. Go ahead and close the dialog. Go ahead and save the simulation. Now let's define the solver settings. To define the time step size, we could use the following expression. This expression means that if the simulation time is less than 0.832222 asterisk 2, then the time step will be equal to 0.002312, which is equivalent to a rotor rotation of 1 degree per time step. However, if the simulation time is greater than 0.832222 asterisk 2, Then the time step will be set to 0.002312 divided by 2, which corresponds to a rotor rotation of 0.5 degrees per time step. In other words, the initial transient part is not of interest for us. Therefore, we're going to start the simulation with a larger time step. Here, we are assuming that the initial transient part is equivalent to the time that it takes the rotor to perform 2 complete rotations, which is 0.832222 asterisk 2 seconds. However, for the purpose of this tutorial, we're going to use a constant time step of 0.0023112 seconds, which is equivalent to a rotor rotation of 1 degree per time step. So under solvers, click on implicit unsteady and set the time step to 0.0023112 seconds. Set the temporal discretization to second order. Go ahead and save the simulation. 6. Definition of monitors and stopping criteria. Under stopping criteria, set the maximum inner iterations to 10 and the maximum physical time to 0.832222 asterisk 4 seconds, which is equivalent to 4 complete rotor rotations. Uncheck the maximum steps. Go ahead and save the simulation. Now right click on reports, new report, force. Rename the force 1 to thrust. Set the direction to Y positive. Check the smooth values. Set parts to blade 1 and blade 2. Create another report that will be a moment report. Rename the moment 1 to torque. Set the axis direction to Y negative. Check the smooth values. Set parts to blade 1 and blade 2. Now let's create an expression to monitor the power generated by the wind turbine. The power is the product of the torque and rotor rotational velocity. Thus, right-click on Reports, New Report, Expression. Go ahead and rename the expression 1 to Power. Click on Definition and set it to 72.0966161 asterisk opening parenthesis 3.1416 divided by 30 closing parenthesis asterisk $, opening curly bracket, torque report, go ahead and click OK. Also set the dimensions to power. Now select all the reports and right click on one of them and choose create monitor and plot from report. Then create one plot per report. Go ahead and save the simulation. Right click on NREL Phase 6 wind turbine simulation and select collapse 3. Now let's create a scene where we can visualize the wake behind the wind turbine. First, right click on Derive Parts, New Part, Isosurface. Click on Isosurface and set the parts to regions. Set the scalar function to Q criterion. Click on value and set the value to 5. Go ahead and save the simulation. Now right click on Scenes, New Scene, select Scalar. Under Scalar Scene 1, click on Outline 1, uncheck Outline, check Surface, set the color mode to constant. Under Outline 1, set the parts to the wind turbine components. Change the orientation to -x -z. You can use the zoom and rotate view options here to put the model in a position of your desire. Now click on Scalar 1, set the contour style to Smooth Field. Now expand Scalar 1, set parts to Isosurface. Set Scalar Field to Velocity Magnitude. Now under Attributes, Annotations, click on Logo and uncheck the box for Visible. Go ahead and save the simulation. To create animation, you have two options. Either you can export the scalar scene for later creating animation from the exported images, or you can create an animated result using the options available within the STAR-CCM Plus. For the latter, you need to store the simulation data while the simulation is running. For this purpose, right-click on Solution Histories, then New, set the name here to ACE-H. Click on ACE-H and set the functions to Q criterion and velocity magnitude. Also set the regions to virtual rotating subdomain and virtual wind tunnel. If we click on update, we can see that the solution data will be stored at each time step. Note that using this option will increase significantly the computational cost, and you need a relatively large memory space in your computer in order to solve the solution history. Thus, to avoid any probable complication, this option is deleted from the simulation file. Under scalar 1, click on color bar and set the font to Times New Roman with the font style of bold. Go ahead and click OK. Set the text position to succeeding. Set the height to 0.055. Set the title height to 0.0475. You can also change the position of the color bar manually using the mouse. Go ahead and save the simulation. Now the simulation setup is complete and you can run the simulation from here. 7. Post-processing. At the end we have the post-processing step. It is worth mentioning that the computations are performed on a desktop computer consisting of 64-bit inlet processors i9 with a velocity of 3.6 GHz and 64 GB of RAM. The simulation takes almost 6 days to finish. Here we have the residuals. Note that to better understand the behavior of residuals, I have set the normalization option of the variables under monitors to off. Here we can see the wake propagation behind the wind turbine rotor. We can clearly see the formation of the tip vortices. Here we can see the behavior of the thrust force and power. As can be seen, they have an oscillating behavior around a mean value. To obtain the mean values of thrust force and power, we discard these values over the first 2 rotor revolutions, and thus the values of these variables are calculated through averaging them over the last 2 rotations. In this regard, this table presents the measured and calculated thrust force and power based on the values of the absolute relative difference between the measured and calculated thrust force and power values. It is safe to say that reasonable accuracy can be achieved using the CFD model outlined in this tutorial for wind turbines simulations. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.